In this video, we will talk about PID. PID is the most commonly used control algorithm in building and industrial automation. PID stands for proportional, integral, and derivative. Here P is proportional, I represent integral, and D represent derivative. PID is a closed loop control mechanism which is very much popular in control industry. In last video, we already discussed what is a closed loop control system. Although dedicated PID controller hardware are also available, but these days mostly PIDs are programmed inside DDCs and PLCs in building and industrial automation. Here is the block diagram representation of a PID control loop. As you can see that this is a closed loop control system where we use the controlled variable as a feedback to the controller, and PID generates the control signal based on this. Let's have a look at it in more details. First of all, we have a set point. This set point is the desired value of our process or control variable. For example, if we are going to control temperature in a AHU, then this set point will be the desired temperature. Then we have a control point. This is the actual value of the controlled variable or the process variable. This is being used as a feedback, and both of these values are then used to generate the error. Error is set point minus control variable. Then we have a PID. First of all, we have proportional term, which is directly proportional to the error, and then we have the integral term, like where our error is being integrated or summed over time and then is multiplied with our gain. Then we have the derivative term, where we are taking derivative of the error, which is like slope of the error, and then we are multiplying it with the derivative gain. PID shown here is a parallel PID. There are other types of PID also which we will not discuss in this video. Based on the error and the gains, the PID generates a control signal. This control signal is then fed to the process, and then again our controlled variable is feedback to the PID. So in this way the PID generates the control signal and control the process in order to achieve our set point. It is not necessary to always use all three terms, proportional, integral, and derivative, together for all of our control applications. Depending on the application, we can also use proportional only control, or we can use proportional plus integral control, or we can use proportional plus derivative control. So it depends on the application which we are using. For example, for temperature control of an AHU or FCU or VAV, we mostly use PI, which is more than enough for this application. Up to now, as you are already aware that PID consists of three different parts, let's discuss about each part in more details. We will start with the proportional. As the name suggests, this part of PID is proportional to the error and is represented by this formula. Here Kp is the proportional gain which is multiplied with the error. With the fixed value of gain, this part is proportional to the error. Larger the error, the larger is the proportional part value. In some softwares or applications, proportional band is used instead of the proportional gain, which is related to the proportional gain by this formula. So as you can see, proportional band is equal to 1 divided by proportional gain. Proportional band can be defined as the amount of change in input required to cause the output signal to change from 0 to 100%. To understand the proportional part of the PID, let's take an example of a temperature control of an AHU by controlling the modulating valve actuator with the proportional only controller. In this case, our set point is 22 degrees Celsius and our proportional band is 4, which means our gain would be 1 divided by 4, which is 0.25. Here output signal is represented by this formula. That output signal is error divided by proportional band multiplied by 100%. Let's consider case 1 where our temperature is 22 degrees Celsius. In this case, error is 0, so the output signal would also be 0. In second case, our temperature is 24 degrees Celsius and our error is 2. So in this case, our output signal would be 50%. In third case, if our temperature rises to 26 degrees Celsius, our proportional band is 4, so our output signal would be 100%. As you can see here, as error keeps on increasing, our output signal keeps on increasing proportionally to it. Also, you would observe one very important thing, that when our error is 4, which is equal to our proportional band, the output signal becomes 100%. This is how we define the proportional band, that it is deviation in the input or the process variable which causes our output to move from 0 to 100%. At error value of 0, our output was 0. So whenever our error became equal to proportional band, our output became 100%. So this understanding of proportional band will help you to imagine that how fast you want your proportional response. So if you increase this proportional band value, if we make it 6, our response would be slower, like the proportional gain would reduce and the output signal would reduce at a less rate with respect to the error. Here is the graph plotting the set point and the control variable for a proportional controller for a specific value of proportional band or proportional gain. Here the red line represents our set point and the blue line shows the control variable. As you can see here that there are several overshoots in the control variable. An overshoot means that the value of the control variable is more than the set point. Also, you will observe that the control variable response is oscillating, which is not desirable. We want something which is like more steady, and we don't want any variations in our temperature. We don't want the temperature to go above the set point, then come very much below the set point and keeps on oscillating. This response is undesirable. So from this response, it is very clear that our proportional gain is very large, or we can also say proportional band is small. So let's increase our proportional band to see the response. As you can see, by increasing the proportional band, the frequency and the magnitude of the overshoots have been decreased and our response have become smooth in the long run. As you would notice here that although after reaching the steady state, there is a difference between the set point and the control variable, which is known as steady state error. This error is always present when only proportional controller is used. So in order to remove this error, we introduce the integral term. Here is the mathematical representation of the integral part. Integration means sum. So here the error term is summed over the time and is multiplied with the integral gain Ki, which is then added to the proportional part to generate the output signal. So here even a small error term would result in increase of the PID output until the steady state error becomes 0. Although integral part also affects the initial response of the PID, but its major effect is in the long term and it acts based on the size of the error and its occurrence time to make the error 0. Some programming softwares use the term integral time instead of integral gain. Integral time is inversely proportional to the integral gain, meaning smaller the gain, larger the integral time. If integral time value is large, response or the effect of the integral part would be smaller, and vice versa. So the effect of the integral part of the PID depends on the integral gain or the integral time. So based on our application, we shall select the integral time or integral gain very carefully. For slow processes like AHU's temperature control, the integral time shall be higher or integral gain should be lower. So initially the proportional part will mostly affect the control output, and then later on slowly this integral part would keep on increasing the output signal and our response would be much smoother. Here is the graph of the previous example with the addition of the integral part. As you can see, after the integral effect, the error started to reduce with time and it became 0 at the end. Here is the response with the decrease in the integral time. Here the error term became 0 faster than the previous case, and also it made the initial response faster and increased the magnitude and frequency of the overshoots in the initial response. So the integral part also have effect on the initial response along with the response in the long term. This should be kept in mind when tuning the PID parameters for your application. In BMS applications, mostly the PI controller is enough and the derivative term is not used mostly, but we will have a brief look at the derivative part to know about its effect in the PID. Here is the mathematical representation of the derivative part. It is directly proportional to the rate of change in error and it tries to make the control output steady. If our control variable is increasing rapidly, rate of change of error would be more, so derivative would decrease the control output. So it tries to make your response smoother.